Hey, everybody. Welcome to our monthly webinar for Georgia ITE. We're very happy to have you all here with us today for our meeting. Share my screen. There you go. Today's meeting will be our September meeting with Kennesaw State University, giving us an update on their program. It's sponsored by Pond, so we're very happy to have them here sponsoring this meeting. Before we get into it, we'll go ahead and go through some announcements we have for Georgia ITE. One of the big events coming up is our G.TEA Georgia ITE golf tournament that is scheduled for October 11th. Registration is open and on our website, so please go ahead and register for that. We are limited to about 144 golfers this year. So if you're interested, make sure you sign up to get a spot. We do have some sponsorship opportunities, and we're looking forward to another great event to help raise money for the scholarships for the G.TEA Scholarship Fund. Additionally, we have the technical exchange coming up soon in October, following day. That'll be with Alabama section ITE this year, and it's going to be at Talladega Super Speedway. So it's going to be an interesting venue. I think it's going to be a great time. We've got a great program set up with speakers both from Alabama and Georgia. We'll hope to have about 4 PDHs available, and it will be a hybrid event. So if you don't think you'll be able to attend in person, there is the opportunity to register online and see the speakers that way. It's going from about 10 a.m. Eastern time to maybe 4 in the afternoon Eastern time. There is additional information on Outside's website, and they are hosting the registration for the event. So if you're interested, please go on there. And then looking forward to next month, our October meeting is going to be a joint meeting with ITS Georgia, and that will be in person at the G.TMC. We'll be celebrating the TMC's 25th anniversary, so we'll be getting an update on that and hopefully be able to do a tour of the facility and see how it's changed in the 25 years since it's been in operation. With that, I want to go ahead and welcome Pond as our sponsor for this month. And I'm going to turn it over now to Richard Fangman to allow him to share his screen and present a little bit about Pond Company. So Richard, thank you very much.
Okay, great. Thank you. And we're really excited to be here sponsoring. Just give me 1 second to get it pulled up here. Sorry. There we go. Oops. Oh, did I get the wrong? Aha. Sorry.
No, perfect. You're good.
Okay, good. Yeah, so really excited to be sponsoring here today with ITE. Pond's a proud supporter of ITE, and we're really excited to be part of this great organization. Next slide here. My thing doesn't want to go to the next slide. No. There we go. Yeah, so just a few quick facts about Pond. So Pond's we got 550 folks at Pond, about 300 of us here in Peachtree Corners, which is our headquarter office. We're ranked number 80 in the ENR top 500 firms. So do a lot of design work across the board. We're first full service, again, A&E firm. The area that I am responsible for is transportation planning and traffic engineering. And we're really excited to be working with a lot of the folks who are IT members on projects throughout the region and the state. We've also got a motto: real people and responsive people and real partners. And we would love to partner with you on our projects, and we take that to heart as we go through our work with all of you. And I guess today we just really wanted to say thank you to everyone. It's been a kind of a crazy couple of years. We've all kind of made our way through, and we want to say thanks to all of our clients out there, and thank you to the partners that we have with other firms. We really love partnering and working together on projects. And we want to thank the students. My son is a student now too, at Auburn University, and it's quite a thing to make it through all the stuff with the pandemic. And so hats off to you guys for all the hard work y'all are putting in, and thanks to our fellow IT members. And
Wonderful. Thank you, Richard. We really appreciate yours and Pond's support.
Sure.
With that, I'm going to go ahead and turn it over to Robinson Nickel and let him introduce today's speakers. So if they want to go ahead and share their screens and get ready for the presentation, go ahead.
All right. Can you hear me?
Yep, we got you.
All right. Well, first of all, I want to say thanks to all the speakers today. We have 3 students from KSU joining us, and the first one is Jelbrin Maharmaj, And currently, Jelbrum is a research assistant and a senior international civil engineering student at KSU. And he came to America from Kosovo, and after he finished his gymnasium in natural sciences, to pursue a bachelor's degree in civil engineering. And after being admitted to KSU, as a scholarship was offered, he has been a full-time student throughout the years and has been working as a student assistant, first for the Department of Career Planning and Development, and then for the Department of Civil Engineering, where he started being more interested in the transportation engineering field. And now he's a research assistant where he does research in automated vehicles, smart intersections, and automated networks. And his dream for a future career is to have a, a job where civil engineering and intersects with transportation and technology. And some other passions besides school is Jelbrum loves nature, rock climbing, and traveling. And with that, I will hand it over to you, Jelbrum.
Great. I am actually very excited to present today because I've been trying, let me see if I'm trying to share my screen. Sorry about this. Trying to fix the problem because the systems and security here in my computer is not allowing me. Usually we use Microsoft Teams every time we present something in school. So it's actually my first time using Zoom.
It should be a green share screen button down on the bottom.
Yeah,
Sounds like it may have some security options. Jelbrum, can you email the group your presentation real quick, and one of us will share it when we click through for you?
yes, I can do that actually real quick.
The calendar invitation, and I'll go ahead and pull it up on my screen so I can help share it for you.
Yes.
Thank you, everyone, for sticking with us through this little technical difficulty. We'll have it back up and running in 1 second.
So the email that I should be sending this to, it's Sean Paul, right?
It'll be cmaddox@sengineering.com. I see yours right here. I'll send you a quick email so you have mine. Well, I knew KSU had such good security standards.
All right, so let me reply to you with the presentation. I did send it. Chris, you got it?
1 second, things coming through. Yep, I got it. Let me get 1 second here. Editing. Screen. Let's get this going. Share. There we go. That should be it. Can you see it?
Yes, I do.
Wonderful. You just say next, and I will click next.
So yeah, thank you for introducing me. Yes, I'm Jelbrum Moarema, an international student from Kosovo. This is my senior year, and I'm expected to graduate in spring of 2022. So this past summer, actually, I had the opportunity to start working for the civil department, where I started doing research with Professor Armigoli. During the research, I studied smart transportation. I studied autonomous vehicles and smart transportation systems, as well as we worked in different systems involving synchronized and autonomous vehicles. Today, I'll be presenting the positive impacts that those systems will have in the future in the reduction of traffic and congestion in urban networks. If you can go to the next slide. So recent advances in communication, computation, and automation technologies have created enormous potential for a profound transformation in transportation system. The advent of self-driving vehicles that can communicate with each other and with smart infrastructure has promoted the idea of a cooperative traffic control in highways and urban networks. If you can go to the next slide. So in the future, highways can potentially have different types of lanes accessibly to vehicles having different levels of automation technology. The advent of self-driving vehicles that can communicate with each other and with smart infrastructure has promoted the idea of cooperative traffic control in highways and urban networks. If we can go to the next slide. But today we mainly have one problem in traffic, and speaking personally, every day that I drive and commute to Kennesaw from downtown Atlanta, there's always going to be traffic or congestion. So that's our main problem. And always to find a solution of a problem, we have to first start and study the problem itself. So let's say, so first I'm going to be starting by explaining this problem in a very simple way. Let's say that you're on green and you're waiting for, let's say that you're in a traffic light and you're waiting for the green light to go. As soon as the green light changes, the first car goes, the second goes, the third goes, and only you in the end to be stuck on a red light. Had the cars accelerated instantaneously, you would have passed through. So coordination, not cars, is the problem. Therefore, because humans have short attention spans and smart reaction times, even if we all tried to press the pedal at once, it would be very unconventional and very challenging. Therefore, the discoordination limits how many cars can get through an intersection. And when backs up to the next, that's when city-sized gridlocks cascade starts to happen and taking forever to clear. If we can go to the next slide. So in general, more intersections equals more discoordination, which equals more traffic. This is the motive behind big highways, right? So no intersection, splits and merges, yes. Intersection, no. No stopping, no coordination problems, no traffic. Intersection outside the highways will still back it up to it. Again, because humans have reaction times limits, how many cars can pass through when the light changes. But even with no intersection, still traffic can happen in highway. Let's say that you're in highway and you break up for whatever reason, something is passing through the road, you break up for just 1 second and then you continue. But the driver behind you is not going to notice that immediately. So then he brakes a little bit harder than necessary, and until the fourth driver in the back comes to a complete stop, making more traffic in highway, which takes a lot of time to clear. So basically, this phantom moves, it's like a snake where it eats cars and leave behind traffic, taking forever to clear. One car slowing down will take in traffic and lasting forever. If the drivers could coordinate and accelerate seamlessly, but they can't, so the traffic will be internal, and we do not like that. Now, in multi-lane highways, if a driver crosses lanes quickly, it's going to cause the drivers behind or on the side to brake, which causes the other drivers on behind to brake as well. So to fix this problem, or now trying to change human behavior, it would not be a solution, because as said before, if we can go to the next slide, as said before, humans have slow reaction time and short attention spans. So another solution that would work would be creating a system in which cars can be synchronized in a way to reduce congestion and to use an automated network. If we can go to the next slide. So a system is proposed for autonomous vehicles to be synchronized and coordinated in platens, where each platen consists of an optimal number of cars. We synchronize arrival and departure of the consecutive platens in crossing directions to eliminate delay at the intersection. When synchronized, the platens of crossing direction pass through each other without stopping in the intersection. So if we can go to the next slide. So how does this work? Well, this requires the approaching platen to arrive at the intersection within when the departing platen in the crossing direction has cleared the intersection. We adjust the acceleration of an approaching platen towards the intersection as the primary control variable of the coordination process to synchronize the arrival of the approaching platen with the departure of the platen crossing the intersection in the crossing direction. So the interplaten headway in the interplaten headway is used for the consecutive passes of platens through each other, where the departure and arrival of the platens in crossing direction must be synchronized as well. For the system developed to work successfully, a marginal gap is added in the interplaten headway. So in fact, if we add the marginal gap, we can say that that can impact the capacity negatively. But because like we try to have a lot of cars passing through the intersection for the short attention, for the short time, so that means that we want a higher capacity. But however, in this setting, it has a positive attribution because it's added to the minimum interplaten headway to make up for the operational error in the synchronization process. If we can go to the next slide. So in case of a successful synchronization, the approaching platen passes through the intersection with no interruption. However, in practice, it is possible that the calculated synchronization acceleration becomes greater than the maximum allowable rate, or causes the speed to exceed the maximum allowable limit. In this case, we increase the platen passing time in crossing directions by merging platens together to bring the synchronization acceleration within allowable range. When the leader of the approaching platen is exactly at the braking distance from the intersection, we check if the trajectory prediction indicates an early arrival. So an early arrival, the approaching platen arrives at the intersection before the departing platen in crossing direction has cleared the intersection. In the case that an early arrival is anticipated, to allow the departing platen in the crossing direction to clear the intersection, so it has to stop, or it has to come to a complete break. In that form, it will give the other platen coming from the other direction to synchronize and to go with the allowable speed that it was synchronized before. In either case, when the platen enters the intersection, it passes through with maximum acceleration to keep the passing time minimized. After clearing the intersection, the platen decelerates back to the network speed. If we can go to the next slide. So the goal of System 8 is to present a system where the optimal capacity is reached. Another important factor is the number of cars that made the platen. The results show that increasing the platen size of the network capacity are not always positive monotonic. So the desirable capacity can be reached only by optimizing the number of optimizing the platen size and the marginal gap, because those two are the most important variables of a system like this. And if we can go to the next slide. So as a conclusion, the safety benefits of automated vehicles are paramount. Automated vehicles have the potential to remove human error from the crash equations, which will help to protect drivers, passengers, as well as bicyclists and pedestrians. Self-driving cars will be able to eliminate sensing and perception errors. And a lot of time crashes happen because it results in drivers' distractions, and autonomous vehicles won't be subject to influence of drugs or alcohol. Also, instead of driving a car, that time can be used to work on different projects, or just traveling definitely will be more convenient. And the best thing and the most exciting thing is that there will be no more traffic or congestion in urban networks. And also, I like speed, so definitely you'll reach at your destination definitely before half the time that it will take for you to drive a traditional car. So yeah, this is my presentation for today. I hope you guys liked it. If y'all have any questions, I'm here.
All right, thank you, Jelbrim. And if anyone has questions for any of the speakers, please add it to the chat box in the YouTube Live, and I'll be monitoring it. All right. I don't see any right now, Jelbrim, so we'll just see if any come in. And thank you for your presentation.
Of course.
All right. Moving on to the next presenter is Isuf Kindo. And Isuf is another student at KSU, and he's a grad student actually in computer science with a specialization in data science and computing. And Isuf, go ahead and share your screen if you can. And he has completed his bachelor's in computing and informatics student at Rowan University before coming to KSU. And while completing his undergraduate coursework, Isuf was the main developer for the PACT team. He was responsible for the design and implementation of the Android app and the web app for the Patient Transportation Center Clinic. Isuf has been participating in the project ever since mid-fall of 2018, bringing to life all ideas proposed by the team. His research interests areas are embedded smart devices, machine learning, and AI. And with that, I'll hand it off to you, Isuf.
Okay, thank you everyone for being here with us today. I'm really excited today to present this. I've been working on this project since last semester for this specific topic on optimizing non-emergency transportation medical system has the core concept of the PAC team that you previously mentioned on my bio. So a little bit more about myself. I know that he already introduced me as a grad student here at KSU. And I also completed a undergraduate certification in French at Rowan University before transferring here at KSU. So can you guys see my slides?
Yes, we can.
Yes.
All right, thank you. Okay, so the team at Rowan University, we won the health hack competition organized by Inspira. And since then, the team has been focusing on building a data collection system to improve our transportation system that we're trying to build. So so before we start, I wanted to actually explain what NEMT is. NEMT stands for Non-Emergency Medical Transportation System. It was designed to help patients get to their medical appointment. And also near the end of 2020, it was officially mandated as an essential benefit for Medicaid. With the passing of the Consolidated Appropriation Act. So why optimize NEMT? With 15.6% of the population in the rural area in New Jersey are aged of 65 or plus. So and with also 16.9% nationwide in 2020. This margin of the population is the most vulnerable to transportation barriers for accessing care. So for example, if for a dialysis patient, for example, if there is they have to go to the medical center at least twice a week for the to meet the doctor to get the appropriate treatment. And due to a lack of convenient transportation, most of the patients missed these appointments, and which has great impact on the outcome of their health. So even in rural areas, even when the NEMT transportation is available, most of the time there is a long wait to get transportation. So NEMT also has like a huge economic impact on the patients. So it has been estimated as that transportation to dialysis facility costs around $3 billion per year to patients, and also it has been estimated that 5.8 million Americans missed or delayed their medical care appointment because of lack of proper NEMT transportation service. And the last estimation is about Medicare. It says that Medicare could also save around $3 billion if they utilize modern transportation technologies. So this is just to say that NEMT has a huge economical impact on society nowadays, and we really need to have a proper system to optimize. We really need to optimize the NEMT. So the current solutions on the market are options on the market right now is public transportation, and like Martha here in Kennesaw, and also we have brokers like Logistics Care, Right Health, Vivo, and also TNS companies like TNC companies like Uber and Lyft. So currently the challenges with these with the ride sharing companies is that most of the ride sharing services today assign drivers by proximity, and most of the drivers are contractors. So lately, we've noticed that the prices are skyrocketing right now for ride sharing because of the scarcity of drivers, and also a lot of patients have been complaining that they all the time there is like a big chance to be driven by a stranger, which most of the passengers don't really feel safe. So we'll go to the next slide. So also public transportation is like the cheapest alternative to ride sharing nowadays. But the huge problem is that most of the patients have to walk to the bus stop, which is an issue with an Asian population, and also, for example, somebody who have limited mobility. And this, so that makes public transportation not convenient for NEMT transportation. And also we have brokers like Logistic Care, which is in New Jersey. They are the primary transportation brokers, and many of the issues that we've encountered while interviewing some of the patients is that it's unreliable, and most of the time they're late for the pickup, and it's really inconvenient. So to sum up, the challenges nowadays is that the current solutions that we have in NEMT are inadequate, convenient, and most of them are difficult to use. And also there is a lack of a relationship link between the right provider and the patients. This is just to say that most of the time it's just the user has only a relationship between the user and Lyft, for example. So it's between the user and the company, not between the user and whoever's going to drive them. So we think that this is a missing link, and it's really important to include that in any next NEMT service. And because of this lack, there is also a lack of knowledgeable drivers. So most of the time you get matched with a driver that actually does not know how to deal with the situation, with the health situation that the patient has. So this makes it this gives a lot of chances for the ride to be canceled because they're independent contractors. So anyway, if they're uncomfortable with doing the ride, they just cancel it and leave. So, and there is also not most of the time it's just a 5-star rating after the ride. There is no actual driver assessment system incorporated with this with the current systems. So the goal of this project is to reduce the missed appointment rate. As a matter of fact, this is the measurement of the success rate in this type of optimization. So this is what we proposed at the Health Act competition, and we proposed a ride-sharing system that also incorporate a closed-loop system, and the closed-loop system would allow us to to make like a relationship network, which is going to also allow us to calculate a relationship index every time we want to pair a driver with a patient. So what is the relationship index? The relationship index is a measurement that would allow us to know, like, okay, in a idealistic ride, the patient would actually know the driver that's going to drop them off, or they know somebody who knows this driver. So it's kind of building a closed loop where then most of the time you see a familiar face when you're gonna when requesting a ride. And we think that by incorporating this closed loop, the patient and driver's comfort is gonna increase. Okay, I think I went. All right, so to do so, we need data, because this project is mostly analyzing the data and finding out what's making these what's impacting these ride sharing company, what's making them inefficient in reducing the miss appointment rate in NEMT. So we started, we built an Android app. So if you see in the middle, we have no, on the far left first, we have the reference code system that we built, which is going to help us build the relationship index, the relationship network first, to be able to calculate the relationship index. So in this reference code system is that a patient requests us to join our system, and provide approval from the provider, and then the driver also requests and it gets an approval from the patient. So it always makes sure that there is a link between a patient and the driver in the system. So with that said, we are actually working on this, maximizing the overall satisfaction in the system. So to do so, we think that it's a multi-objective optimization system. So this is actually a work in progress. I'm still working on this. This is actually what I'm working on this semester, is developing a mathematical model to be able to increase the satisfaction level every time we match a driver with a patient. So well, we think that it's going to be maximizing the satisfaction level is going to be related to historical ratings. It's also going to be related to the ride cost compared to the current market ride cost. It's also going to be related to the preference match. And it's also going to be related to our relationship index that we built from the closed loop system. So in the multi-objective optimization system is first of all, it starts with finding a feasible set. And in our case, the feasible set would be a pair of drivers and patients that a pair that passes the constraint of, like, first of all, having a good relationship, and also based on the cost, which incorporates the time to complete the ride, time to pick up, and compared, and also passes, like, let's see, the cost compared to the current market cost. So basically, the feasible set is a set of drivers with the current ride that are competitive. And once we find the feasible set, every feasible set has a point in the objective space, and this is where we try to maximize. So let's say, for example, we have 10 drivers that are willing to complete this ride. In the optimization set, we find the best driver within that set. And to find the best driver, we just use a Pareto front line. This front line is found by eliminating all the dominant solution. And on the line, every solution on the line is a solution that is not dominant. So it means that, for example, a driver on one, for example, can be as close as possible to the user, and but at the same time, they don't have a strong relationship. It means that the patient is not really familiar with them. It's some sort of like a friend of friend. And at 2, we have another driver that is probably somebody that they know, but at the same time, they don't have the right equipment to execute this ride. Maybe they're far away, or maybe they just don't have for the accommodation that the patient needs. And right at the middle, we have somebody that is kind of related to the patient, for example, and that is also close enough to drop them off. And in that condition, this would be the Pareto optimum solution. And another variable that we thought was important also to add, because it's is the driving style assessment. This is actually from a paper that I've read online, and in that study, they recorded the X and Y, Z acceleration and made this graph. So if you look at the what's it called, the black dot is the expert driver, which means that this is like idealistically how you would drive. This driver is the one we use to measure any other driver, to categorize any other driver. For example, the blue driver could be categorized as a smooth driver or an aggressive driver. So we thought that by including this variable in our system, it would also allow us to have a better insight on the ride. So we are also going to use a machine learning algorithm to help us find a relative satisfaction level every time before we match. And this is going to help us maximize the overall satisfaction. So, and we have a feedback system that would also, like after every ride, we're going to have a little survey to gather all the data and to retrain the model every time. So the model gets better at predicting their relative satisfaction over time. So the next step is collecting more data, because this is mostly a data science project, and a data science project is as strong as the data that we have. So after we collect the data, the mathematical model I showed you guys previously is going to be changed mostly because of more study that we're going to do on the data. So completing the mathematical step would be one of the after in this semester, it's going to be the last step. So if you guys have any questions, this was what I had today. So it's still a work in progress. We haven't, we have to still collect more data to still, do more analysis and see if like the theories that we had would work. For example, the multi-objective maximization system. So thank you for being here. And if you guys have any question, I would be delighted to answer.
All right. Thank you, Yusuf. And like you said, if you have any questions, please add them to the chat box in YouTube, and we'll go over those at the end. And with that, we will move on to the next student. Mafan Akpak is a PhD student in the Interdisciplinary Engineering Program at KSU. His research is geared towards smart infrastructure with a great focus on vehicle to everything, or V2X. Mafan has received a master's in mathematics from Drexel University in Philadelphia in 2005. Following that up, he received another master's in electrical engineering technology at Southern Poly State University in Marietta. He received another master's in information technology from Southern Poly in December 2014, and then another master's in software engineering from then KSU in 2019. So he has, in addition to all those degrees, an 8-year experience in designing and building cable TV head ends, general hardware, and software migration while working with Cisco systems. So with that, I'll hand it off to you, Mafan.
Hey, Mafan, I think you're still on mute. We see you talking. hear you.
Oh, I'm sorry.
There you go. We got you now. And your screen's
Yeah,
good.
sorry. I
So,
was on mute. I'm so sorry. So my name is Mfon Okpok, as I mentioned, and I'm a PhD student in the interdisciplinary engineering program at the Kennesaw State University. So my research interest is in intelligent transport systems. Well, as we all know, the intelligent transport system involves other facets. There are so many other facets. So I'm not going to be jack of all trade and master of none, right? I want to narrow down to a vehicle to everything. Before getting down there, I want to introduce challenges that we have and what is going on in transportation system. As we all know, sometimes the plane land on the road, right, unexpectedly. And also, let us look at the fact that sometimes there is outage, traffic outage, as you see below, natural disaster that is uncontrollable, things that we don't control. It is in the hands of the mother nature sometimes, right? Plane crash, disaster. But in the midst of all this, we want to look at ways of making the system smart, regardless of all these challenges, right? So with that being said, I'm looking at effective monitoring of transportation system using artificial intelligence. For instance, there is no traffic light. The drone should be available, right, to talk to the autonomous cars, and the drone should be able to be deployed, or we can deploy drones to stand up there and say, hey, this car, you have to go. The other one needs to stop. So moreover, the drone will be handling traffic during that time until the Department of Transportation or whosoever, whichever county is able to fix the traffic light, or probably maybe there is power outage. So the drone should be able to handle that effectively, you know, kind of instead of a policeman, the drone should be there talking to all these cars. So with that being said, it is important that we share video within the network, images, and also the police can stay in their office and see the real-time video. What happened if the power went out? So in that case, so the power is down, there is storm, hurricane. So in that case, we can use the video from the car to talk to the police or to send to the police, where they can use that video to understand what is going on. Not only the police though, the ambulance need to know what's going on in the street. Even the cars needs to know if there is gallop or there is pothole or there are challenges, active shooter. So the video of all what I mentioned should be presented to the ad hoc system so that the law enforcement agent or the insurance company should be able to capture this video. Keep in mind that as the cars are going, they're going to be having insurance, and who's going to ask questions when the police arrive, or maybe something happened, a car failed. So we need to get video. Video is important, right? There is network. Again, if somebody is in the rural area and there is no medical, they have to drive miles. There is an accident, they have to drive miles to the clinic, right? So we should be able to make the doctor available in the car, in the emergency car, right? Or a drone should be there to help transmit the video. So these are all things that we have to think of while we are deploying the video to X, or we are looking at autonomous vehicle, or, you know, there are so many circumstances that could happen that we need to prepare for, right? All right, so let's move down. Well, there are some related challenges. One of the challenges is bandwidth limitation, right? Of course, you know, if you have multiple cars streaming video, there's going to be bandwidth issues. That's number one. And the second thing is, as the car is progressing, right? Say, for example, I have 5 cars spread within the road network. The car that is closer to, if I'm transmitting video, the car that is closer to me will tend to have high quality video. If I tend to transmit the high quality video down the street, well, the car that is not close to my car will have distorted video. What I'm saying in essence is that there's what we call decay of signal, right? The RF signal is going to decay. And as the RF signal decays, I want to assure you that we'll be having very poor quality video or images. So the challenge now is, how do we solve that problem? Now, another challenge in the video system, having read so many literature, is that there's so much bias when it comes to video. Everybody thinks that the driver needs to sit down there and look at some kind of Michael Jackson singing, you know, and that's not the case with video. People think that there should be some kind of a video servers out there where kids will stay behind the cars and then press a button and then the video on demand will come up. Well, that's cool. It's also a good idea. But we are talking about how can we use video to keep our road safe, and how can we use video, say, when there is road incident, the insurance company, the police, and the medical doctor, of course, can appear and they talk to and check the situation in the van as they are driving down there. Because sometimes, as we know, if the injury is severe, before getting to the hospital, say the patient may even die on the road. So deploying video in intelligence system or in the car or in the ambulance will also help the doctor to appear and then see the situation and know what to tell the nurses in the ambulance or whosoever is, is always accompanying the patients. Well, so my greatest challenge also is that, or our greatest challenge with video is that there's so much bias. Everybody talk about intelligence system, cars talking to each other, but nobody talk about how video will be modulated or how video could be effectively transmitted from one car to another car when there's emergency. So for example, there is fire down the street. I should be able to tell the firefighter, hey, be careful as you're driving. Look at the intersection. There's a car that potentially could get to the intersection and you're going to jam the car, so be careful, right? I should tell the firefighter, well, or the sheriff, as you are getting down there, I see there are some active shooters. Please be careful as you're driving down there. Here are the pictures. I should tell the police, okay, hey, something is happening out there. Here is the picture. Do you know these guys? And then there should be artificial intelligence that should analyze those images and say, hey, this guy's an active shooter, be very careful. Police is going out there and then, so there's so many use of video that is being ignored in few literatures. So I want to bring up that to light. Again, so with that being said, my research is going to be, we expect the research outcome to be more of site link, PC5 site link optimization so that it can accommodate video, right? And then another thing is we have to adjust the bit rate. So here is the second one is the greatest challenge that we are having. If I am saying that the closest car to me is going to have clear video, how about the car that is having less signal? How are we going to be able to transmit video to those cars that is far so that they will know, hey, it's raining over here, be careful, or there is traffic and people are hurrying to job. How can I transmit video of the pothole, or how can I transmit video of the incident to the car that is maybe a mile behind me so that they will not panic or probably, know what is going on up front? How can I transmit video of what is going on in the road to keep our system safe? So with that, looking at the bit rate, I have to adjust my bit rate according to the strength of the signal. So that's where the challenge lies. So as the signal decays, I have to adapt with the signal decay and then move my video. Is it going to be during that time? Am I going to send high definition, low definition, standard definition video? And by the way, what is the aspect ratio that I'm going to transmit? So these are all things that we are trying to resolve. Keep in mind that artificial intelligence also, say for instance, I have a drone up there. The drone will look at the situation and will be able to analyze and then come up with better solution. So these are areas that we are focusing on. Okay, let's look at that image. If we don't look at quality image, how to send quality image to some extent, if I keep sending high definition, of course, we know that it's going to be more of a high compression scheme. So there's a tendency for it to pixelate. So you have some kind of crazy looking video, but before it gets to the car that is not close to me, or the receiver or the device that is not close to me. So using adaptive video, we will try and gauge, at least to our best, to make sure that before the video gets to destination, there is a reasonable, we've tried our possible best to present quality video to the user before everything goes away. So can you imagine, I want to send to police this guy right here, right? And I'm using a constant bit rate, right? You can see that the guy is trying to move. If I send this to AI, it may not be able to. I mean, I'm just using this as an example. the AI system will have difficulties in identifying these guys. So we want to make sure that as the signal decays, we try our possible best to send at least a standard definition instead of high definition, or we kind of look at the way of a different, a bit rate kind of control, so that we can at least send tangible video per distance. That way the receiver can see it. So here is it. For instance, looking at the adaptive video delivery, the blue car that is closer to the red one by the side can send high definition. But if the blue car wants to send a video to the guy down the street, it's definitely going to be degraded more or less as standard definition video. So how are we going to make this happen? How are we going to adjust this? How are we going to calculate the distance? How will our system be smart enough to know, hey, I don't want to collide. I don't want to create collision. I don't want to consume all the bandwidth, but I also want to send video to that guy that there's an accident or there is a pothole. I also want to send a request. Is there any medical doctor around here? There is somebody that is dying here. Can you come up? And then the medical doctor will appear and talk to the patient, right? So these are the kind of things that we are looking at. And to this end, I would like to ask if anybody has a question for me.
All right, thank you, Mafan. And thanks to all the speakers today. These are really interesting topics. And now we will open up the floor for questions. If anyone has questions, feel free to type them in the live chat. And I actually had a question, I guess, for Isuf regarding the presentation on the non-emergency medical transportation.
Yes.
That's a really interesting algorithm, and I think a good example of the crossover between transportation and public health. I guess in your research, have you had any examples of where there's just really not a good match of, you know, a patient that just is located in a almost like a driver desert, where there's just not any good matches within a reasonable amount of distance? And, you know, if so, how would like what would be a recommendation for that, like a subsidized bus service or, you know, something like that?
Oh, okay, thank you for your question. This is actually a great question because before we started the development of the Android app, we had a good survey at the Inspira Health Network, which they sponsored this project, by the way. So most of the patients in rural area, for example, elder patients that live by themselves. So the first problem is that most of the time they don't know how to use these modern technologies to get a good ride to go wherever, to go to the medical appointment, for example. So the issue with that is in rural areas, there aren't like the availability for ride-sharing companies is very low. So for a patient living in that situation by themselves, it's complicated to get a ride. So most of what the current solution is like logistic care does, that they allow patients to just call in and reserve a ride. But these settings nowadays are it's difficult to guess where the patient is going to be and where to drop them off. So these companies most of the time rely again on ride sharing companies. Even though they can find a ride, it's going to be like it's going to take a long time for the driver to drive from, for example, in like a urban area to this rural area to pick them up and then drop them off. So there is a disconnection over there. So there is no service actually right now that is that he always knows exactly that this patient has to get here at this time every time of this week, and have a good scheduling system for them. So that's what we're trying to achieve over here. So by having like their ride every time, even if it's a call in like for the first time, we're gonna make sure that every time they have somebody that could drop them off in the community, for example. So every time we have a patient in a given community, the system is going to make sure that there is always a driver nearby that's able to drop them off. So it's the point where I think I didn't mention it in the presentation, but this is where our system is trying to hire drivers. Actually, it's not just going to be only independent contractors, because the issue is that independent contractors drive whenever they want. But if you have a system that has a combination of these two, like we still have independent contractors. For example, if we want to hire, if a patient has their son that, every time they can drop them off, we could hire that person as an independent contractor and build the right to the Medicaid or to the insurance company, for example. So in this case, we're utilizing independent contractors. But what about the time that we don't have any independent contractor available? This is why we have also the system where we hire all people in the community, or we hire people that, for example, the medical facility recommend, for example. So that's basically the core concept of the project.
All right. Well, thank you very much. I guess that's about all the time we have. Chris, did you have any other announcements before we close up?
I think that's it. Thank you, Robinson, for helping orchestrate today's meeting. And Richard, yours and Pon's commitment to sponsorship, we really appreciate it. We're very happy to have the students again active in our organization. And thank you all very much for taking the time out of your day to come and speak to us. And we hope to see you at some of our events when we finally get around to meeting in person again. With that, I'll go ahead and say thank you, everyone, and we can adjourn today's meeting.
Thank you very much.